Welcome back everyone to what is quantum computing. In the previous video we had went over the normalization of qubits and we had done a little fun Python activity. In this video we're going to be going over representing bit operations with matrices, and we're also going to do another fun activity in Python at the end. So in this video we'll be going over the operation on qubits, matrix multiplication, the flip operator, representing the flip operator with the matrix, and then bit operation with matrices in our Python IDE. So what are like performing an operation on a qubit mean, right? And how does that operation affect the states of our qubit, right? So if we remember, our qubit is x of 0 plus y of 1, right? Now, when we do perform any type of operation, we would be changing the linear combination variables x and y, right? It would essentially be changing the amplitudes of the certain states, right? And we could still be changing x and y, but x and y would still uh, uh, be true, where x squared plus y squared would still be equal to 1, right? And to really see this change in operation, you could do this through something called matrix multiplication. So matrices are the language that are used to describe the change in qubits, and they both change the values of the x and the y, right? The amplitudes, right? So in this scenario, we have a row and a column, right? The row is a separate matrix. The column is a separate matrix. Essentially, when we want to multiply it, we would get an output like this. How do we get this output? Well, we need to multiply the row and the column in the condescending order. So we would do 1 times 10, 2 times 20, 3 times 30, right? 1, 2, 3, 1, 2, 3, right? And then again, same thing over here, right? We would do 4 times 10, 5 times 20, 6 times 30, right? So we would do first row times the first column, second row times the first column. Then we would do the first row times the second column, plus the second row times the second column, right? And then, so this right here, everything over here is for the first column, and this is for the first column. And then you'd simplify it, and then you would get 2 columns, 2 rows, right? So as we were mentioning about the operators, right, the certain operations, one operation you can make to change these amplitudes would be the flip operator, right? Which changes the state of the qubit accordingly to where, let's say, x of 0 plus y of 1 can just be y of 0 plus x of 1. So essentially, x is now y and y is now x, right? And both states will still be equal to 1, right? So now I'll demonstrate an example of the flip operator in Google Jamboard, okay? So let's go here. All right. So let's grab our pen or marker. So let's say we have x. Let's make that a x of 0, right? Plus y of 1, right? Now, as we had mentioned, the same thing, right? Same thing can just be equal to so we'd have 0. Think of it like this, like that. We'd have 1 of 0 plus 0 of 1. Please bear with my handwriting here. But yeah. So we have these two components now, right? Now let's say if we wanted to flip this, okay? So if we wanted to flip this, we would have our first column, x, y, right? And this essentially, so x and y, this x and this y, these two linear combination variables are equal to 1 and 0, right? It's equal to 1 and 0, these two qubits. Now let's say if we were to flip this linear combination variable. So again, I just wanted to say that this qubit is just a representation of the actual qubit here, but it has a number, right, 1 and 0. So if we were to do the flip operator, we would simply just be changing it, right? Switching 1 and 0, so it'd be 0 and 1, right? So the flip of 0 would just be 1, right? And the flip of 1 would just be 0, right? Changing, right? Vice versa, basically, right? So yeah. Now here's what we're gonna do. Why don't we actually try this out um, with some real complex numbers? Okay. So here's what we're gonna do. Let's move on to another Jamboard, and let's grab our pen. All right. Now let's say if we wanted to, let's say if we had 1/√5, right? Complex number, 1/√5. That's our x. 1/√5 is 0, right? Plus, all right, now we're gonna need to have our y, right? Root of, sorry, just in something of 1, right? Okay, so you might be wondering, okay, well, what is a y supposed to be? What is this? What is the value of the variable that's supposed to be in this area, right? Okay, so how will we find that, right? So one thing we know, right? One thing we know is that x squared. So again, this is just x and this is y. X squared plus y squared is equal to 1. So if we wanted to find y, oops, let's just make that a y right there. Yeah. So if we wanted to find y, we would simply just want to do this, right? We have x squared, we have y squared. Now we just want to do our plugins, right? So we'd have y squared is equal to 1 minus x squared, right? So in this scenario, x is 1/√5. But what would 1/√5 squared be? Well, that is simply just, okay, if you basic algebra, right, you multiply a rational root by a rational root and you would get the actual value, right? So root of 5 times root of 5 would just simply be 5, right? So you just have 1/5, right? So same thing here, right? So it would just be y squared is equal to 1 minus 1/5, which is just y squared is equal to 4/5, because 1 is just 5/5, right? So it's 5. And here we'd have y is equal to square root of 4/5. Okay, awesome. All right, we have found our y, so we could just plug it back in here. 4 divided by 5. Okay, now we can flip this again, right? We could flip this again, like just like we had discussed, right? We could still flip this, like this flip operator over here, right? 1 0 0 1, right? So here's what we'll do. Just gonna erase this, right? And then so if we flip it, it would look something like this. All right. So again, we would have 1/√5. Oops. It's that root of 5 is supposed to be like this. 1/√5, and instead of 0, it would be a 1, right? We're changing the states. Plus root of 4/5 of 0, right? We're just changing the states, right? And if you can compare this, we simply just did the flip of this, like we just applied the flip operator. And this is what we will be later on doing in Python, right? So this is simply how we would be using the flip operator generally, okay? But now, if we move on to the next one here, we want to try to explain the flip operator as a matrix, right? So to represent it as a matrix, right, there will be a matrix of 2 rows consisting of 0 and 1 and 1 0, right? Just 2 rows. And then there will be a matrix column that is just x and y, right? And our goal is to get a flip product of y and x. So instead of going from x and y, I would go to y and x, right? So, and remember, y and x are our states amplitudes, and we're just flipping them, right? So as a result, the total probability will still be the same. It's still going to be constant, right? So hence x squared plus y squared would still just be equal to y squared plus x squared, right? So why don't we go to our lovely old Jamboard over here, right? Okay, so we have our matrix here, and this here, okay, this here is a matrix representation of our flip operator. Flip operator. Ooh. Ignore the spelling, but yeah. And then we would have our x and y, our amplitudes that we are trying to flip. And simply, it should just go y and x. All right, now you might be wondering, okay, well, how did we get this, right? So this is just the amplitude. Okay, so now we're going to apply the rules of matrix multiplication. So remember, this right here, these are rows and this is a column. So what we're first going to do is we're going to multiply each value in the row by the first column, right? So we do 0. Let's go here, 0 times x plus 1 times x. All right. And so 0 times x, 0 times y, not x. We don't want to get that confused, right? Because it's supposed to be in condescending order, so it's 1 times y. So if we have our y here, our y, it would just be, so 0 times x is 0 plus 1 times y, so that's just equal to y. And if we were to do 1 times y, 1 times x times plus 0 times y. So 1 times x is x, and 0 times y, let's get that equal, yeah, is just 0, right? So it would just be y and x, right? So that, ladies and gentlemen, is our flip operator. As you can see, that's how we just visualized, not even visualized, we just showed live on how we can use the matrices to flip the amplitudes of a state, right? Now what we're going to be doing is we're going to take this one step ahead and doing this in our Python IDE, okay? So yeah, so we're going to be doing our bit operations with the matrices in Python, right? Now that we've covered multiplication, matrix multiplication, the flip operator, and the bit operation, we're just going to use those elements and write a program that represents the flip operator using matrices, right? And in this scenario, we'll be using something called arrays, okay, to create a flip array and an array with our x and y. So a flip array is just simply just a flip matrix, right? And an array with our x and y. That's also another matrix, right? And the output is an array with the amplitudes flipped, all right? And again, don't stress, we're going to know what an array is. So if you do need to just follow this link over here to open your new collab. But I already have my collab set in my tabs back over here. So again, back over here, these will be our two separate matrices, okay? We will have our flip operator matrix right here, and then we're going to have our x and y amplitude matrix right here, and our output will, is trying to get the flip, right, of y and x, right? So these are going to be our two separate arrays, okay? So, all right. So let's just clear this out here. All right, so first, why don't we go over what a Python array is, okay? So an array is a special variable which can hold more than one value at a time, right? But also in arrays, we're going to have to be using our NumPy library, right? Our math NumPy library. So we're just going to be doing this. Going to be doing. Oh, and by the way, remember our normalization of qubits program right here. So we already have NumPy import here actually, so we don't really need to putting in. So we can just put in another cell here, and we're just going to do, let's say if we had, we can have anything, right? We would have, let's say, ARR is equal to just array is equal to NumPy dot array, and then first of all, there's two types of arrays. There's a one-dimensional array and there's a two-dimensional array, right? So this one-dimensional one, we could just have it. So again, in this case, array is a function, right? That is in the NumPy library, right? So we just have, let's say, 1, 2, 3, 4, 5. And these are just 1, 2, 3, 4, 5 are separate items, right? They can even be strings, right? And if we just print this array, we get an output of 1, 2, 3, 4, 5, right? Oh, okay. It says name NP is not defined. Okay, maybe we should just have to import it right here because we do not want to forget to import our library, right? If we don't import our library, then how can we access these functions like array, right? So yeah, now we have 1, 2, 3, 4, 5 exactly. Now let's say if we want to use a 2D array. Now a 2D arrays are where we're going to be using our matrices. Okay, they are usually used to represent a matrix or like 2D order tensors, right? So here's what we can do is we would have two of these kind of arrays essentially, right? Which is why it's called a two-dimensional array. So we would have this and a column. So we have 1, 2, 3, 4 as one array. Maybe we could have another array as 5, 6, 7, 8. And then let's see here. All right. Okay. So and then we just need to put in another bracket here just to represent that it's a 2D array. And then if we print this, exactly, now we get something that's in the form of a matrix, right? So this is, again, what is used to have these elements, right, of matrices, right? Now, there's 1D array, 2D arrays, 3D arrays, you can make as many as you want, right? Now, in order for our actual program, we are going to be using two-dimensional arrays, right? So what we're going to be doing here is just this up. So we are going to be essentially having two matrices, and we're going to be, one matrix will be a flip operator matrix, and the other one will just be our complex numbers, our amplitudes, our states. And essentially, we're going to be using another function called matmul, which multiplies those two matrices, and that important to us because it comes from the NumPy library, right? And it also does the matrix multiplication, right? So first, we can just have one qubit, right? A Q1, and then we're just going to have that equal to a certain array. So we're going to np dot array there, and now we're going to use. Now this is not going to be two-dimensional array. This is just going to be a single array, a 1D array of our complex numbers. Okay, so remember, complex number can just also have like a rational number as its denominator. So we can have one np dot square root, let's say 3, right? And then we would do comma, right? Because we would have two or 3, right? And then we'd have np, because essentially we're gonna have two numbers, one as your x and one as your y. Divided by, and then we'd have np dot square root, and something maybe like 3, right? And now to really finalize this as our array, we need to put our brackets here. So this is kind of what it should look like right now. Let's see here. P.array. Yep, seems just about right. Okay, so now that we have there, we're just gonna print Q1. Show. Okay, so that's our array right there, our matrix of our two numbers of the two amplitudes of x and y. Now we're gonna have Q2, which is our actual flip method, right? So actually, we're gonna have Q2 for a matmul. Why don't we just label it as flip? So we're gonna have flip is equal to np dot array. We need that, and this time it's gonna be a two-dimensional array. So we have here, we're gonna have another bracket to represent the two-dimensional 0, 1, 1, 0. Okay, and then let's just make sure that our flip is correct. Yep. Okay, so that's our flip operator right there. Okay, now what we're gonna do is we're gonna matmul it. All right, we're gonna use matmul to multiply both of these matrices, right? The flip by the. So we're gonna have Q2 equal to np dot matmul, and then flip Q1. All right, so here, let's write this down. Okay, so matmul is essentially it's a multiplication it's matrix multiplication. So manual is matrix multiplication, and so it takes matrix, the left matrix, and then it takes matrix on the left and multiplies it by the matrix on the right. So essentially, it would really just be flip times Q1, right? It would just be the flip matrix times the Q1 matrix, right? So if we print Q2, boom, we have the same thing, right? 0.5777, all that, 0.811. So this is our Q1, this is our starting matrix, and then we did the flip operator, and boom, it just flipped. And actually, we used matrix multiplication here in real time using matmul to really show that, right? And it's literally just these two numbers flipped, right? Now, let's say if we wanted to prove that this is still constant with the law of probability, and we just wanted to add it, it would still be, they would still be equal to one, right? So this pretty much sums up how matrix multiplication works, right? And representing the bit operations, right? So until then, I'll be seeing you all in the next video. Thank you.